Hello, we have come to the last module of this course. So, the last module is superconductivity that we are going to discuss now. Many of you are familiar with superconductivity, but for the sake of completeness, we will go through a formal description of the phenomenology of superconductivity that many of you know. Then we will go into the theoretical aspects of superconductivity. The electrical resistivity of many metals, alloys and compounds, they drop suddenly to 0, perfect 0, when the specimen is cooled to a sufficiently low temperature. This phenomenon is called superconductivity. This was first observed in 1911 by Kamerlingh Onnes. This was 3 years after he could liquefy helium. Before liquefying of helium, which is about 2 Kelvin temperature at which helium can be liquefied, before liquid helium being available, there was no possibility of discovering superconductivity or knowing that something like that existed. At a critical temperature, we call it Tc, T critical, the specimen undergoes a transition from a state of normal electrical resistivity to a superconducting state. Below Tc, it is superconductor. And for T greater than Tc, the material is a normal conductor. Now, looking at this, so far what we have described, you may have an impression that superconductor is just like a normal conductor with the resistivity 0, but that is not the case. There is a certain difference between normal conductor with exact 0 resistance, if that existed, although it does not exist. If that existed, a normal conductor with exact 0 resistance and superconductor, these two things would still be different. There is a significant difference between these two, and we will come to that discussion. Let us go to an experimental survey of superconductivity, the phenomenology of superconductivity. In the superconducting state, the DC electrical resistivity is 0 or close to 0. That persistent electrical currents have been observed to flow without attenuating in superconducting rings for more than a year until the experiment was stopped. So, the current does not stop even though there is no electric field, which should have happened provided there is no resistance. Therefore, this clearly is the case of no resistance. And just like the dramatic electrical properties, superconductors also possess dramatic magnetic properties, where it differs from a normal conductor with exact 0 resistance. The magnetic properties cannot be accounted for by assuming superconductors at normal conductors with 0 electrical resistivity. Bulk superconductor in weak magnetic field act as a perfect diamagnet. What do we mean by perfect diamagnet? That means whatever magnetic field is applied, nothing enters the material in its superconducting state. So, the interior has no magnetic field. no magnetic induction in the interior of a superconductor. And this happens up to a maximum threshold of the external magnetic field, applied magnetic field, beyond which the magnetic field penetrates the material. At the same time, the superconducting property is also lost. So, it remains in superconducting state and allows the magnetic field to pass through. That does not happen if the magnetic field is sufficiently large to invade the material, then the superconductivity is killed. Now, when a specimen is placed in magnetic field and is then cooled through the transition temperature Tc for superconductivity, the magnetic flux originally present is ejected from the specimen. We have a specimen at a temperature T greater than Tc. Now, we are cooling this material and bring it to T less than Tc, and during the process we had some magnetic field, external magnetic field applied in the material. Now, as soon as we cooled it below Tc, the magnetic field would be expelled of this material, and this kind of effect is called the Meissner effect. And this is very interesting. So, here we discuss some properties of superconductivity. Superconductivity occurs in many metallic elements, alloys and intermetallic compounds and doped semiconductors as well, and it has a very varying range of critical temperature. YBa2Cu3O3, this compound has a superconducting critical temperature of about 90 Kelvin, pretty high, and rhodium on the other hand has a tiny superconducting critical temperature which is 0.001 Kelvin. Silicon can become superconducting at a moderate temperature of 8.3 Kelvin at 165 kilobar of pressure, which is extremely high pressure. Foreign paramagnetic impurities can superconductivity, also a strong external magnetic field can destroy superconductivity. And this is the Meissner effect that we were talking about. If we have the temperature above the critical temperature, the magnetic field passes through this material here, this blue material, and as soon as we bring this temperature below Tc by cooling the material, the magnetic field is expelled. The field lines move outside the material, it cannot penetrate through the material. Meissner effect shows that a bulk superconductor behaves as if the magnetic field is 0 inside the specimen. We obtain a particularly useful form of this result if we limit ourselves to long thin specimen with long axis parallel to the applied magnetic field Ba. Now, the demagnetizing field contribution will be negligible. So, the magnetic field can be written as Ba plus mu naught m in the material, and as we described the Meissner effect, this magnetic field has to be 0 inside the material. That means m over Ba applied magnetic field, this equals minus 1 over mu, and that has to be equal to minus epsilon naught c squared. The result B equals 0 cannot be derived from the characterization of the superconductor as a medium of 0 resistivity. That is how superconductor is different from a normal conductor of 0 resistance. Now, let us consider Ohm's law. Ohm's law tells us that applied electric field E is rho times the current, rho is the resistivity. And J is the current density. We see that if resistivity goes to 0 while the current density J is held finite, then E must be 0. So, if rho goes to 0, J is finite, we must have E going to 0. Now, let us recall a Maxwell's equation, which is also known as Faraday's law, that is del B del T equals minus curl of the electric field. Recalling this, 0 resistivity means del B del T must be 0. That means there is no change of the magnetic field with time, but that does not require the magnetic field to be 0. That means absolute 0 resistivity does not require the magnetic field to be 0, which can be the case, but not necessarily. And by research, we also know that the flux through the metal cannot change on cooling through the transition. The Meissner effect suggests that perfect diamagnetism is an essential property of a superconducting state. We expect another difference between superconductors and perfect conductors, defined as a conductor in which the electrons have infinite mean free path. When the problem is solved in detail, it turns out that a perfect conductor, when placed in a magnetic field, cannot produce a permanent eddy current screen. The field will penetrate about 1 centimeter per hour, but in superconductor that does not happen. Then we discuss about type 1 and type 2 superconductors. So, type 1 superconductivity is abruptly killed beyond the critical magnetic field, as shown in this red curve here, red lines. Here H is the external magnetic field applied and minus mu m, that is proportional to magnetization. If we have a type 1 superconductor, then the superconductivity sustains up to this much, that is Hc, critical field, and then it is abruptly killed, and it cannot resist the magnetic field beyond this value of the magnetic field. But if we have type 2 superconductor, then there are two different critical fields. Up to the first critical field, the magnetization keeps on changing linearly, and then it increases linearly. Then beyond this field, there is an exponential decay in the magnetization, or negative of magnetization to be more precise, and then after beyond the second critical field, the superconducting property is completely killed. So, this part below Hc1, that is absolute superconducting state, beyond Hc1 and below Hc2, that is a mixed state, and beyond Hc2 it is a normal metallic state. There are other properties of superconductors, like we can talk about heat capacity, which is lower in superconducting state and decreases with decreasing temperature. There is an energy gap in a superconductor, which is a correlation gap, not at all like the band gap in a band insulator, and this gap is observed around the Fermi level. If we consider different isotopes of an element, if that element is superconducting and has a critical temperature, that change, so different isotopes will have different critical temperature for superconductivity, and if we mix these isotopes, that superconducting critical temperature varies smoothly as a function of mixing.